Hi everyone, I'm Tong Wu from the ECE department at the Research Center. Today I'm very happy to present my research in the CECS faculty seminar, and my research topic is physics via safe AI. First, let me briefly introduce my lab. The lab is Intelligent Control and Sustainable Energy System. And my group include one PhD student and another incoming PhD student who is now a system assistant in my group. And the current research areas in my group include universal grid AI, graph AI methods for the power network applications. Certainly, it can apply other network systems, and safe AI methods for the control of network systems, as well as differential neural network for the optimization of electricity markets. In terms of teaching, I will design a new graduate courses in modeling and artificial intelligence, which will introduce the advanced graph AI and large language models methods for the network systems. So you can introduce this course for your students to choose. And now, let me review the AI in energy sector application first. In general, AI can apply to energy systems planning, detection, control, as well as the physics-aware machine learning models for the power systems. For planning, I have utilized deep learning to optimize utility commitments and schedule power generations to accommodate wind power. In the detection area, I have used random forest algorithms for adaptive power grid for detection, applied transfer deep learning for the voltage stability assessments, and employ the neural network embedding within the neural network to recover the missing data in power system measurements. As for machine learning, I have improved AI by considering graph signal processing and the power system physics to design a machine learning model to capture the spatial temporal correlations of power system measurements. And by using this technique, we are able to revisit the tasks and significantly improve their performance. Finally, when we come to the control tasks, I have built physics via safe AI, considering the physics hard constraints into neural networks for the safe network control and robust EV control. First work I want to show in detail is physics-aware AI in power systems. In order to consider the AI methods for the control of three-phase unbalanced distribution networks. First, we have a naive representation that is a Laplacian matrix. But in most scenarios, it is not enough to capture the complicated spatial temporal correlations of power system state variables. Then we can have the physics-aware representation that consider the linear relaxation of power flow equations in the real domain. Now, let us see how to integrate the power system representations into neural networks. And this is the neural networks, and this is the graph representations of the power systems. And we can construct this perceptron, which includes the graph convolution plus a nonlinear activation functions to construct our perceptron. But for very complicated tasks, we can have multi-layer graph convolution neural networks. For example, we can choose a physics-aware graph convolution neural networks for the reinforcement learning control of solar power inverters in a three-phase unbalanced distribution systems. The control action is active and the reactive power generations of PV panels. And the objective here is to regulate voltage magnitude into the safe region. The result shows the proposed graph recurrent neural networks and the graph convolution neural networks converge to a higher rewards, where the other fully collected neural networks and the graph convolution neural networks cannot converge. This is because these neural networks have a large number of redundant trainable parameters, ignoring the spatial temporal correlations of power system data. This increases the complexity of the reinforcement learning when searching for the optimal solution. Now we are ready to generalize the physics-aware graph AI into the complex domain by embedding the complex value power system admittance matrix into neural networks. This involves working with a complex value of graph signal X and the graph shape data S and a trainable parameter HK that is also a complex value. And we can have the complex value activation function, which can activate the real and imaginary part respectively. And we can extend this to cover spatial temporal graph convolution neural network, which can cover both the space and the time in the complex domain. In this way, we directly integrate the admittance matrix of the either three-phase unbalanced power grids or the single-phase transmission network into the power systems. And in this work, we have proved the complex value of GCN transfer theory. This theory shows if we have small perturbations in the graph shift or rata S, we can have a similar response for the results, which provided a theoretical guarantee of the transfer learning. In addition, we also proved the stability theory. This is about the robustness to the perturbations, both in the grid environment and our training parameters. Importantly, they can ensure our GCM maintains stable with some perturbations. And another interesting work is safe reinforced learning for the control of safety critical systems. And when we talk about the optimal control, there are two different communities that actually work in the same issue of optimal control. So the first one is a reinforcement learning community and sort of recent deep reinforcement learning methods. And the advantage here is this deep neural network in the deep reinforcement learning are real expressive and can provide real performing policies for the future uncertainty. But the con here is these techniques, generally speaking, does not come with the feasible and safe guarantee. As a result, they can produce unsafe action and leads to the blackout of power system. And on the other side, the optimization theory the community is working on the similar set of problems. What this community says that the provable feasibility guarantees are very important. However, these methods require lots of assumptions and relaxations on the control policies. On top of that, this community needs to solve different scenarios every time they meet new data. For example, the model predictive control. So it is hard for them to scalable to the large-scale network control with high resolution time series data, for example, the renewable energy integration. So the question here is, can we somehow combine the advantage of two sorts? Can we somehow improve the performance by using some sort of technologies that deep reinforcement use and guarantee the feasibility? So in order to achieve these targets, we need to focus on the constrained deep reinforcement learning based on the actor credits. And in the basic reinforcement learning, an actor just interacts with the environment by taking actions. Each action changes the state of the environment and result in a reward, which indicates the effectiveness of these actions. And the agent wants to maximize the total reward over the times. And but most of the time, this deep reinforcement learning allow unsafe actions due to the complicated safe action space description in the constraint optimization problems. So our idea is to combine the deep reinforcement learning and the constraint optimization to derive a constrained AI actor. So we have the primary problems to minimize the loss. The loss is also the maximize the rewards. And we also have a dual problems can gradually move the feasible regions from the unsafe part to the safe region and to ensure the safe actions by the reinforcement learning. And we can model this constrained reinforcement learning as a non-convex, non-differentiable Lipschitz continuous function. And we can prove the convergence that can always converge to a suboptimal and certify all the physical hard constraints. And now let me introduce my research highlights. First, my research in the physics where AI is motivated by the no-pass graph signals such as voltage measurements of power systems, which have strong spatial temporal correlations. Based on our graph signal processing techniques, I embed Ohm's law in a complex domain into the neural networks and propose physics-aware graph AI methods to demonstrate the better performance compared with other neural networks for the network inference and control tasks. And I further prove the proposed physics-aware graph AI methods are robust to graph perturbations, and this framework can be easily extended to other cyber-physical systems by considering specific laws of the physics using the tool of graph signal processing. Another important area of my research contributes to extending AI to safe AI. For example, the constrained reinforcement learning considers the physics hard constraints of the power systems. This approach combines the expressive capability of deep reinforcement learning and deep neural network with the feasibility guarantee provided by the optimization methods. And these safe AI tools can have a broader impact in the safety critical systems, including power systems and transportation systems. Finally, I view the safe AI from three viewpoints: the feasibility, stability, and the robustness to the worst case adversarial attack. Finally, I will introduce my future research directions. So for my future work, I will work on next generation AI methods with graph signal processing that were suited for use in energy systems and other cyber-physical systems and impactfully deployed on the ground. So the first research direction is to consider graph signal processing to enhance the model interpretability. So we don't want the neural networks like the black box. We want to see the graph signal processing to get which features will take effect in our specific tasks. A second direction is derive the robust graph signal processing or graph neural network to the adversarial perturbations or the cyber-physical attacks. The second one is derive the graph convolution neural network with dynamic graphs. For example, consider gating mechanisms for the topology change or some graph dynamics. Another important direction is to expand the safe AI areas by considering the consider other robustness criteria in a control society. For example, we can consider safe AI and robust AI with Lyapunov stability criteria for the voltage control or the frequency control. We can also consider how to make the neural network or the AI methods is convex to the optimization problems. So most of the time we use neural network to solve optimization problems. We can also use convex optimization problem to solve a neural network tasks that can ensure the global optimal and the convergence. The broader effect is the physics or VSC for other safety critical systems. Thank you.